Okay, let's take a look at Dijkstra's algorithm formally, but first do a little bit of review. Earlier I indicated that Dijkstra tended to think of problems in concurrency or parallelism, and that may have had some influence on the way his algorithm works. So I just wanted to kind of quickly review that. So remember, we start at San Francisco, and then we look at all of the possible outgoing flights. And we pick the one with the minimum distance. That kind of makes some intuitive sense because we're trying to minimize total overall travel. So we'll take the one that happens to be closest to us. And then it's kind of interesting. We've kind of now are considering outgoing paths from both of these. So we had our list of places we could get to in their total distances, our distance to Boston, our distance to O'Hare, and our distance to Dallas. And then we started also including the distances that go through a two-leg flight going through LA to Dallas or LA to Miami. And we also ruled out some of these. So by the time we got to basically our third major step of this algorithm, we had sent crews out to kind of 3 different cities here, and we'd identified specific paths. We'd found the smallest possible path to LA and the shortest possible path to Dallas as well. And then we were able to consider all of the outgoing paths from each of those. So it was almost like we had a person stationed in each city that we're completely done processing. And we can pick up and use whichever of these outgoing arcs happens to be the minimum total distance from San Francisco. Okay, so let's take a look at Dijkstra's algorithm. So we're going to break this into 2 parts. So the first part is the initialization phase. So in the initialization phase, we'll go through and process each individual vertex. So we'll mark it as unfinished. So basically, we still have to process every vertex in our graph as soon as we're done with initialization. And we'll look at each vertex, and if it happens to be the start, we'll indicate we already know how to get there. The distance is 0. Otherwise, we'll indicate the distance is infinity. So that's all there really is to the initialization. Mark everything as unfinished. Set up the initial distance as either 0 for the start vertex or infinity for everything else. Okay, next the algorithm processes each vertex. So it does that with some sort of a loop. As long as there are unfinished vertices, it's going to go ahead and retrieve an unfinished vertex, but it does it based on the smallest total distance. Again, this is what we're trying to minimize, so it kind of makes sense. If we're trying to minimize the smallest overall distance, we'll process things that are, in a sense, closest to us. Okay, and then we'll look at each of the outgoing edges from that vertex, so from vertex V to vertex U, and we'll see if the amount of work it takes to get to V plus the work to go from V to U is better than any known distance to U. So basically the idea is if the distance going through V is better than anything that we already know, any other path that we already know about how to get to U, we'll go ahead and update our distance to U. And this is also where we'd keep track of that predecessor node if we were interested in tracking paths. Okay, after the for loop is done, after we've processed each outgoing edge, we're done processing that vertex, so we'll go ahead and mark it as finished. So that's necessary for our while loop to eventually terminate. Okay, and that's pretty much all there is to Dijkstra's algorithm. Okay, so I want to go back and look at the core of the while loop one more time. This line here where it processes each vertex with the smallest overall V, that's really key. Earlier I kind of described this as something that's almost happening in parallel. It's almost like there's an additional explorer stationed at each of the vertices that we've already completed, and they're there ready to go to the next vertex that is overall the closest. So it's this line of the pseudocode right here where all of that happens. Okay, so I also wanted to focus on this if statement. So this particular component of the process is referred to as relaxation. Basically, we start off with a really pessimistic estimate of distance. We started off with our distance being infinity, and we continually see if we can refine or relax that estimate, get it to a better and better estimate of actual distance that's required. So this kind of overall process of seeing if we can do better and then updating our value to use any sort of new and improved path that we found is relaxation. While we're here, I just wanted to take a quick look at a few other details. So as usual, Wikipedia has a pretty complete overview of Dijkstra's algorithm. They classify it in terms of various different types of things. So notice that it's referred to as a search algorithm where we're searching for an optimal solution. Notice that it's also referred to as a greedy algorithm. We'll come back to that in our last module. As usual, it gives some performance stuff. We'll come up with that on our own in the next component of the lecture. Also, there's a pseudocode that looks very comparable to the pseudocode we've just looked at. It has the relaxation component. It has this idea of finding the vertex that's best, that's got the minimum distance as we are going through and processing each thing. Okay, notice that it mentions something about using a priority queue, so we'll come back to that as we start talking about time complexity. Okay, so if Dijkstra's algorithm falls in the class of algorithms that solve the shortest path problem. So Wikipedia also has an OK article giving several different shortest path algorithms. So Dijkstra's algorithm is listed first here. Notice that in their description of Dijkstra's algorithm, they specify that it's for non-negative edge weights. So we'll look at that too. They also mention some other algorithms that solve shortest path problems of various sorts. So Bellman-Ford algorithm can handle negative weights. So that's one of the ways that it's distinguished from Dijkstra's algorithm. There's a technique called A-star search. So A-star search uses a heuristic to speed things up. If you take an introduction to AI, CSE 347, you'll examine AI A-star search and some of the requirements for it to be guaranteed to be effective. There are also other variants that solve slightly different problems. So Floyd-Warshall solves all pair shortest paths. So not single source shortest path, but all pair shortest path. And then there's Johnson's algorithm and Viterbi's algorithm that solve slightly different variations and have slightly different trade-offs.